Everyone got my email on time? Yeah? Do y'all miss me? I know y'all miss me. It's okay. So I hated to have to do that, but what happened was another faculty member had something come up and they couldn't teach their class on Monday morning, and it was a Calculus 3 class. And so there's only like 2 of us that teach Cal 3 here, and so I'm the only one who could sub that class. So that's kind of what happened. So I could have got a sub to come in for this class, but I figured I would make you watch 30 hours of videos. Yeah? Just 1 hour, right? So I hope that went okay. Let me get your test back to you. I'll call your name, come up and grab these. Milena? Kiani? We'll wait. Evan? The grades I don't believe are on here, but they're online. And I think what you can do is just subtract, like the numbers that I counted off, just add them up and subtract it from 100. That's your grade. Andrea Lopez? Rebecca? Oh, there you are. Okay. Is it Christine Gonzalez? It's Christine? Yeah, Christine. Stephanie? There you are. Victoria? Heidi? Kiana? Here. Yes, there you are. Kiana? Caroline? Kristen? Devin? Elena? Kayleen? Rodrigo? Macy? Sylvia? You got it? Sorry. Christian? Vince? Itzel? Zeke? Josh? Hold on. I don't know why I got you confused with Frank. Josh and Frank.
I forgot to square.
And Sylvia. There you go. Okay. Okay. So the third exam, I actually do not have the data for the exam. You know how I usually show you what the average was and stuff? I don't have that. I don't know why I forgot to do that, but I'll show you that next time. All right. Now I also have quizzes, but I can pass those back at another time. Okay? So if you have any questions over the exam, get with me after class or during my office hours if you want to talk about any of that. At this point, you should have a pretty good indication of where you are in the class in terms of your grade. So that's the third exam. We have 2 more. Now, unfortunately, the next exam is scheduled after the drop date. So anybody who thinks that their grade is on the border where they might feel like they want to retake the class, I don't remember if this even applies to anybody, but just know that your grade's not going to change much between now and that date where you have to make that decision. So if you're kind of not sure, come talk to me and I can help kind of guide you and help you make what decision is best for you. Okay? Any questions or anything before we get into this? No? Everyone's good? Sure? Okay. All right, so I asked you to watch a video, right? 2 of them. And how did that go? Fun? That good, huh? That good. All right, well, let's see if you actually understood any of it. So I'm not going to quiz you. I'm just going to put a function up here on the board. So how many of you think that watching videos like that and then doing homework online and taking tests online would actually work for you? Anyone? Like, because there's online courses, you know, you can do, and basically that's what you do is you watch lectures and then you do all your work online, yeah? Some people like that, some people don't, so. Sorry my videos aren't as exciting as some of the other stuff on YouTube, but. Okay, so what was the video about? Polynomial functions. So the whole idea here is that we know how to graph lines, linear functions. We know how to graph parabolas, which are quadratic functions. And the goal of the videos was to get us to be able to graph polynomial functions. And there were a set of steps for this. So let's list down what the steps are. What was the first step that we do for sketching or drawing a polynomial function? Make sure it's polynomial, right? First thing, that's what we've been doing from the very beginning. Like, if you're asked to graph a line, make sure it's a line. If you're asked to graph a parabola, make sure it's a parabola. So, poly, I'm just going to put poly, question mark, is it a polynomial? So, is this a polynomial? Why is it a polynomial? What makes it a polynomial? Degree. So you have all these terms, right? Addition, subtraction, and then you have things that have x's in them. And the powers on those x's are either 0, 1, 2, 3, 4, 5, 6, 7. It's only these counting numbers, right? Like if you had -3 right there, this wouldn't be a polynomial. Or if you had a fraction right there, like 1/2, it wouldn't be a polynomial. To be a polynomial, you have to have nice counting number powers on all your x's, right? So this is a polynomial. So is a quadratic a polynomial? Quadratic is a polynomial, but we're trying to open it up now to where you have your highest power is not 2, it can be 3 or 4 or 5 or 6, and really there's no limit to how big the power can be. So it is a polynomial. What's the second step? Okay, so you find the degree of the polynomial and the leading coefficient, which I abbreviate LC. So in this particular problem, what is the degree of the polynomial? 5. Now the degree, by definition, is the highest power of x that we see. So we have a power of 5. That's our degree, right? 5. And then what's our leading coefficient? 1. And that is always the number in front of the x that had the highest power. So in this case, the degree here is 1. I mean, sorry, the leading coefficient is 1. Okay. What now? Determine the end behavior, right? Determine the end behavior. So when you have a degree that has 5, that's an odd number, right? And when your leading coefficient is 1, that means it's a positive, right? And I showed you a table that you had to use to figure out the end behavior. And that table I would provide you on the test, all right? So I'll put the table on the side here, just so we can continue with this. The table kind of worked like this. I forget, did I have degree on the top? Degree up here? So degree is either going to be odd or even. I don't recall which way I did it. Even first, I think? Okay. Even, odd. And then over here is your leading coefficient, and it's either positive or negative, right? So what happens if you're even and positive, you go up and up. Even and negative, you go down and down. Odd, positive, you go down, then up, and then the other way around here. And then the middle, we don't know. Okay, so I talked about that, right? Okay, so for us, we have an odd power, or an odd degree, right, and a positive leading coefficient. So what is our graph going to look like? What is the left and right behavior? Left side's going to do what? Left side's going to go down. Right side's going to go up. In the middle, we don't know. So we're working off of this right here because we have an odd degree and a positive leading coefficient. Does that make sense to everyone? You sure? Okay, what's next? The X-intercepts, right? So again, I don't recall. Was this a separate step? Was this step 3 or was it part of 2?
No, it was step 3.
It was step 3. So step 4 is the X-intercepts? Okay, thank you. So the X-intercepts. So how do we find the X-intercepts for a polynomial function? Set it equal to 0. And this is normally the hard part, okay? So let's take this thing and set it equal to 0. I'm going to do that work right here. I take x to the 5th minus 8x to the 4th plus 16x cubed, and I set it equal to 0. And now I'm trying to solve this equation, right? So how could I work on solving this equation? This is not a quadratic, it's not a linear, right? It's a polynomial equation. So ideas? Yeah, just do what we've been doing in the past, right? GCF, right? Let's try and factor the left-hand side. So what is that greatest common factor?
X cubed.
X cubed. Everyone see that? We can pull an x cubed out, right? If we do that, we will be left with, on the inside, let's see, x squared minus 8x plus 16 equals 0. And now we continue to try and factor, right? And what's inside that parentheses is a quadratic and can be factored, right? So for this inside piece, you would use like the AC method. Something like the AC. And I'm not going to do it because I'm going to expect that you could. You would put 16 here and you put negative 8 here and you mess around with the numbers and I think you get like negative 4, negative 4. All right, so that's the method. But the next line after you do this, so there might be some work you have to do to get to this next line, should be x minus 4 times x minus 4 equals 0. Now this is where things get a little weird with polynomial functions. We have set it equal to 0, we have factored it, and we will be able to set those equal to 0, right? But there's something else with polynomials that we have to pay attention to. And what's that? What's that? Yeah, it's something, and what does that tell us? Whether or not our picture will cross through or bounce, all right? So when you look at this, right here, I'm going to continue up here. Do y'all see that these are the same factors? That's x minus 4 repeated twice. So the way I want to write this is like this. X cubed times x minus 4 squared equals 0. So the squared just means that I have 2 of those factors, right? 2 of these. You have to do that before you move to the next step. So if you ever see 2 of the same factors, you want to put them together, all right? Now if this was plus 4, let's just say, x minus 4, x plus 4, then we couldn't put them together, right? We just leave them split up. But because they're the same, we can put them together. And now what we do is we set each of these equal to 0. X cubed is 0. X minus 4, you could say squared equals 0. We're going to try and solve these 2 equations. So what would x have to be so that when you cube it, you get 0? 0 itself, right? So the solution to this is x is 0. And then over here, is it obvious what x would have to be to make this whole thing 0? What would it be? 4, right? If x is 4, 4 minus 4 is 0, 0 squared is 0. So this would give you x equals 4. So how many x-intercepts do I have? I have 2 x-intercepts, right? At 0 and at 4. However, we still have not dealt with this bouncing crossing thing, right? Do y'all know what I'm talking about? Bounce or cross? I have to sneeze, maybe, hold on. Okay, it decided not to do that. All right, so what do I look at to determine the bouncing or the crossing? You said exponents, so like tell me for this one, how are you going to determine if I bounce or cross here? You're going to look at that cubed power, right? See if this is odd or even. In this case, it's odd, right? And what does odd tell you? If it's odd, what do you do there? You cross. you cross. All right? And then this one, you look at the power, right? The power on this factor was what? 2, right? So that's even. And what happens if you have an even power? You bounce. Okay? So if you didn't watch the videos, you're probably like, what the hell, cross bounce? What is he talking about? So now we're ready to draw it, right? That's the last step. We just put all this together. So I'm going to come over here and draw my picture. I have my x and y axes. And I don't get super detailed on this, okay? I just draw my x and y. I put my two x-intercepts, 0 and 4. These are dots on my graph. 0, 1, 2, 3, 4. Here we go. We have 2 dots. What comes next? What's the next piece of the picture I want to draw? The end behavior, okay? The end behavior. So what do we know about the left end of this graph? What's it supposed to be doing over there? It's going down, and then on the right side it's supposed to be going up, right? So what I know is, like, if these are the only 2 points I have on my picture, I know that after this point this way it's supposed to go down, right? And then after this point over there it's supposed to go up. So I'm just going to kind of way out here, I'm just going to draw kind of an arrow going down. That's the left side of my graph. And then over here I'm going to draw an arrow going up, and that's the right side of my graph. And now I'm going to just connect the dots, okay? But I have to pay attention to what's happening at each of my x-intercepts. So at 0, I'm actually supposed to draw and cross through that x-intercept. So I'm supposed to go, I'm not going to do it yet, just kind of think about it first. I'm going to draw it, and then I'm going to cross through, right? And then I have to get back to this point, and when I get to that point, what am I going to do? Bounce off. So I'm going to draw it, and I'm going to bounce off that point and come back up. And now I just kind of put it all together. There we go. Does that make sense? Bouncing versus crossing. That's the 2 differences between those 2. Now, I don't recall if I mentioned this on the video. I didn't watch the video, I'm sorry. Would this be incorrect if some, like, let's say you drew that and then some other student drew this? Which one of those is right? Both of them are right, okay? Both students get full credit for this. We have to, all our pictures have to have certain things in common. They all have to have the same left and right behavior. They have to have the same intercepts, and they have to have the same crossing and bouncing happening. Otherwise, how high you go is up to you. If you really wanted to know how high this went, well, you know, like with parabolas, we could find the highest point and lowest point, right? Here we can't. You have to take calculus to do that. So in calculus, my calculus class, tomorrow I'm going to be talking about how to find this point. So it's taken us how many weeks are we in now? 10 or 11 weeks into the semester. It's taken us that long in Calculus 1 to get to the point where we're going to be able to find those points. So it's beyond the scope of this class is what I'm saying. So how high you go with that, don't worry about it. All right? That's it, we're done. What do y'all think? Yes? Okay. Now, there are some problems that I gave you. I'm going to do one more, and then we're moving on. In that problem, I gave you the function, and we had to factor it, didn't we? We had to factor it. But another way you're going to see problems presented to you on your next test will be where I give it to you factored. Something like this. So it's already factored for you. So there's good news and bad news with this. The good news is that when you get to the part where you do x-intercepts, you don't have to do the factoring, right? Right? And you also know that at this x-intercept, you're going, because that's an even number, you're going to be doing what here? Even power means bouncing. So I'm going to bounce off that x-intercept. This x-intercept, I'm going to odd, that's cross. And at this x-intercept, I'm going to bounce. So see, all of that you don't have to actually figure out. It's all there. What's the part that's now more complicated? The end behavior. So the end behavior, see, when you look at that right there, your leading coefficient, or sorry, your degree and your leading coefficient aren't obvious. We have to determine those. Okay, so first step here, is it a polynomial? Yes, okay. Second step, I need the degree and the leading coefficient. Now, to do this, there's kind of a shortcut. The shortcut is you just look at the powers you have here. So this right here is really like an x to the fourth. Well, it is x to the fourth, right? It is. But this one is not x cubed. It's x plus 1 cubed. But if you were to multiply all this out, okay, so you don't have to do this, but if you were to do x plus 1 times x plus 1 times x plus 1, if you multiplied all this out, the highest power you would get out of this would be an x cubed. So when we look at this, all we have to do is say, hey, look, this kind of behaves like an x cubed. And this one kind of behaves like what? What is that one? What's the highest power of x that you're going to get out of that one? X to the sixth. Agreed? So if I have something that's x to the fourth, x to the third, and x to the sixth, and I'm going to multiply them together, then what's the highest power of x going to be? So if I just had those two, what would the power be? X to the, is it 7th or 12th? 7th. You're adding the exponents. Just think about, this is x times x times x times x. That's x to the fourth, right? Times x times x times x. Ooh. How many x's do you have? 7, right? So that's an x to the 7th. And then when you put this one with it, it's x to the 13, right? So all you're doing is adding all these powers together, and you get 13 as the power. So that means if you were to multiply all that crap out, the degree here would be 13. Does that make sense? Okay. Now what about your leading coefficient? This one's a little bit tricky, but in this case, in this particular problem, it's not bad. When you look at the coefficient of the leading coefficient of that one, that's 1, right? So there's really like a 1 here. There's a 1 here, so that goes there. And there's a 1 here. So if we were to multiply 1, 1, and 1 together, we would get 1 still, right? So our leading coefficient will be 1. And I'm not going to make it any more complicated on the test. I'm going to keep it simple like this. I could put, like, right here, I could put 2x plus 1, and then things become a little bit crazy. But I promise you it'll be a 1 every time on these problems. Okay, so are there any questions on this part, this step 2? Because I'm moved to step 3 now. Step 3. All right, end behavior. So we have odd again and positive. This is kind of boring. It's the same one as last time, isn't it? Down and up. Odd degree, positive leading coefficient. Odd degree, positive leading coefficient. All right, step 4. The X-intercepts. So we have to take each factor and set them equal to 0. So I'll just do it. I'll do it right here. I have to set x to the 4th equal to 0. I have to set x plus 1 cubed equal to 0. I have to set x minus 7 to the 6th equal to 0. And again, all of those you should just be able to look at and tell me what the x-intercepts are. So what about the first one? X has to be 0. Second one. To make this 0, I need that to be a negative 1, right? So negative 1. And then this one, 7. Almost done. Just got to figure out whether or not I bounce or cross now. So what will I do here? Look at the power, right? What is it? Even. Even means bounce. Here, look at the power. It's odd. Odd means cross. Here, look at the power. Power is 6, right? Even. Even means bounce. The biggest mistake I see students make on these problems is that when they're trying to figure out the bouncing and the crossing, they look at the number instead of the power. So they look at 7 and they're like, oh, 7 is odd, so I'm going to cross here. No, it has nothing to do with the 7, it has to do with the exponent. All right, so just be careful with that. And we're ready to draw. It's fun, right? Thank you. Okay, here we go. Starting with what? X-intercepts. Okay, so just make sure you get these in order. Here's 0. 7, 1, 2, 3, 4, 5, 6, 7. And -1. Right there. There we go. So there are X-intercepts. My end behavior is next. So left end's going to go down. Right end's going to go up. And now I need to connect. So I like to kind of trace this through without writing first. At -1, I'm going to cross. And then when I get to 0, I'm going to bounce. And when I get to 7, I'm going to bounce. So I think I'm going to do something like this. I'm going to come up. I'm going to cross through. I'm going to bounce off. And then I'm going to bounce off again and come back up. So cross through, bounce off, and come back up. And maybe I need to erase and redraw it, but good enough. All right? So we're done with polynomials. Think you can handle that? Okay, I'm going to give you a, I don't have it right now, but I'm going to email you a practice assignment for you to do with these. What I'm going to do is I'm just going to pull a couple of problems off my past tests and give those to you as a take-home assignment just to practice. Because the homework in the packet I don't want you to do. So don't worry about doing any packet homework for this section on polynomial functions and their graphs, all right? So in my video, do I talk at all about why polynomial functions would be useful or no? Remember how I talked about parabolas and parabolas, you know, cell phone towers and flashlights and cell phones, right? All this stuff, right? Polynomials I didn't really talk too much or little? Yeah, anything that goes, you know, up and down, you know, stock market, things like that, income for a company, anything that fluctuates, you have a polynomial can be a good model. Because with polynomials, the higher the degree, the more like curves you're going to have in it. So you could have like the degree could be 10, and then you could have 8 or 10 curves bumps in it. All right, so now we're going to move on. That's the sun. Okay. We're going to move on to the next topic. Rational functions. We're down to the last 3 functions. We've done linear, quadratic, polynomial. Now we're going to go for rational. After rational, we have exponential and logarithmic. So the rational functions are the most complicated out of all the functions we're going to do. These are the most complicated ones. And again, because this is 13-14, not 14-14, we are going to take a light approach to it. But I'm going to ask you to think. Like you're going to have to think a little bit here. All right. So a rational function, what is it? What does it look like in terms of the formula for it, I guess? Any function that is a polynomial divided by another polynomial is a rational function. All right, so we all know what polynomials are, right? I mean, we just did them. Polynomial by itself is just a polynomial. But what if we have 2 polynomials and we divide them by one another? Now you're looking at a rational function. Some examples. Let me show you some examples of what a rational function would look like. So an example would be the function f of x equals x plus 1 over x squared minus 2x minus 8. That is an example of a rational function. Now, let's check that it is. The top by itself is a line, isn't it? And all lines are polynomials. What's the degree of this polynomial? What's the degree? 1, right? Okay, I'm dividing that by another polynomial. This polynomial has a degree of what? 2, right? So it is a polynomial divided by a polynomial. Yes, the bottom is a quadratic, but it's still a polynomial. So that's an example. I could take this, I don't know, I could do like this, x cubed minus x squared over, you know what, let's make that x cubed minus 4x squared over x squared minus 8x plus 9. That's another example of a rational function. And you can imagine you could go crazy with this, right? Any polynomial you could think of over any polynomial you could think of. I mean, it's kind of like endless on what you could do here, right? Let me give you one more example. No, don't want that. Let's change this to 27x. All right. Another polynomial over a polynomial, right? Okay, now when it comes to rational functions, think about this. Every rational function you ever have, your numerator, the top, is going to have a degree to that polynomial, right? That has a degree, it's 1. This degree is, on the bottom is 2. Okay, look at this one. The degree on top is 3, the degree on the bottom is 2. This one, the degree on top is 2, bottom is 2. So when you think about all the different possibilities of rational functions, there's only 3 different cases that you could get in terms of degrees. Either the top has a smaller degree than the bottom, right? Or the top has a bigger degree than the bottom, or they have the same degree. Do you all agree that there's only those 3 possibilities, right? That's actually going to turn out to be something that we use, all right? So does everyone see that? Degree of the top smaller than bottom here? Degree of top is bigger than bottom. Degree of the top same as bottom, right? So we'll use that in a second. All right, before we go and I start giving you steps on how to graph these, let's actually take a look at one. Let's graph a rational function right now and talk about its properties. Because we know lines look like this, parabolas look like this, or they open up, and polynomials look like these little weird stock market things. But what do these things look like, right? So I'm going to give you a one of the most basic rational functions out there. This is probably that is it right there. That is like, if you're trying to show people or talk about rational functions for the first time, this is the one we like to show them because it illustrates some of the cool properties of rational functions. 1 over x. So do you agree that the top 1 is a line? It's a horizontal line. So it is a polynomial, because lines are polynomials. And the bottom is also a line, right? That's the diagonal line, x. So this is still a polynomial over a polynomial. It's just not very interesting, right? There's not a whole lot going on in this one. So I'd like for us to graph this, right? So the way we're going to graph this is I'm going to put the graph over here, and we're going to do this old school way. We're going to do a t-table, where you plug in x, and so you get to pick some values of x, and we're going to plot points and just try and get an idea of what it looks like. All right? So let's start out with 1. What would happen if you plug 1 in? 1, you get 1 over 1. So you get 1, right? So this is a point on my graph. It's the point 1 goes in, 1 comes out. So if I go over to 1, I go up 1, that's a point, right? Okay, what about if I plug in 2? What do I get when I plug in 2? 1 over 2, right? Which is a half. So that means I have the point 2 goes in, 1/2 comes out. 2 goes in, 1/2 comes out. What's going to happen when I plug in 3? 1/3, 4, 1/4, 5, 1/5, yes? What happens when I plug in 10? 1/10. What if I plug in 100? 1/100th. What if I plug in 1,000? 1/1,000th. What if I plug in 1,000,000? 1/1,000,000th. What if I plug in 1,000,000,000, gajillions, gazillions? 1 over a billion, jillion, zillions, right? Is that still a tiny little number? It is, right? It's not 0. Do y'all agree or no? So no matter how far out I go here, these numbers get smaller, but they never actually reach 0. It's impossible. 1 divided by a big number is still a positive number, yes? So what happens is this thing starts to flatten out. The curve's starting to flatten out, getting closer to 0, but it never gets there, so we put an arrow, and then what we do is we put, I don't have a ruler in here, but we put a dotted line out along the x-axis. And what the dotted line represents is that this curve is getting closer and closer and closer to the dotted line, but never touches it. You never actually get there. All right? This has not happened before, has it? Have we ever had a function behave like this? Think about lines. Lines, you know, on the left and right either did that or like that, right? Parabolas either did that or like that on the ends, right? Polynomials, it was that, right? The ends always went up or down on everything we've studied. We've never seen a function where when you come to the end, it just kind of, it's almost like the red dotted line is like a magnet. I always like to think of it as like a magnet. It's pulling the graph towards it, but it never allows it to touch it. And this has a name. This is called a horizontal asymptote. This is a weird word, asymptote. A-S-Y-M-P-T-O-T-E, all right? Horizontal meaning horizontal. Asymptote means that your function gets closer and closer to it without touching it, all right? Make sense? So it looks like these rational functions can have these things called horizontal asymptotes, which we've never seen, right? Okay, let's plug in some other numbers. I mean, we kind of get the idea what happens if we plug in numbers out this way. Let's plug in some numbers on the other side. How about -1? What would happen if I plug in -1? I get 1 over -1, which is -1, right? So that means you plug in -1, you get -1. So I have a dot here. What if I plug in -2? -1/2, -3, -1/3, and so on and so forth, right? So you're going to have something similar happening on this side. -2, at -2 we're at -1/2, -3 we're at -1/3. So your graph is going like this, and it's crying, but it's getting closer and closer to 0, but the outputs are negative instead of over here they were positive, right? So it's like -1, -1/2, -3, -4. It's getting closer and closer to 0, but from the bottom instead of from the top. That make sense? Okay. What have I conveniently avoided here? I've conveniently avoided one number. I've not plugged it in on purpose. 0. Why am I not plugging in 0? If I plug 0 in, what's 1 divided by 0? It's undefined, right? Which means that there is no graph at 0. This has never happened, right? This has never happened. Lines, parabolas, polynomials, there was never a number you could not plug in. You could always plug a number in to a line, parabola, and a polynomial. This is the first time we're getting division by 0, right? And if you look at these 3 examples, anytime this bottom is 0, I have a problem, don't I? Anytime this bottom is 0, I have a problem. Anytime this bottom is 0, I have a problem, right? We have division by 0. So we know that you can't plug in 0. So let's try something else. Let's try something over here, like, how about this number, 1/2? What happens if I plug in 1/2? We do 1 over 1/2. What's 1 divided by 1/2? What's 1 divided by 1/2? 2. So in other words, when you have 1 over a fraction, you can just flip it over and it just becomes 2 over 1, which is 2. So at 1/2, I'm up 2. Sorry, here. At 1/2, I'm up 1, I'm up at 2. What would happen if you plug in, let's do something closer to 0, like let's plug in 1/4. What happens if you plug in 1/4? Where are you going to be? At 4, right? So 1/4, I'm up here at 4. Okay, where am I at 1/10? At 10. Where am I at 1/100th? So if I get really close right there, 1 over 100, plug that in, what's it going to spit out? 100. Can I get closer than that? I can get even closer. I can go to like 1 over 1,000, and where would I be? 1,000. So what is this function doing? It's like taking off. It's like blowing up, right? It's just like, yes? But you can't be at 0, can you? Like you cannot plug 0 in. So what we get here is not a horizontal asymptote, but a vertical asymptote. All right, so we have vertical asymptote. So I told you that the horizontal asymptotes, I like to look at those as like magnets, and they pull your function towards them, right? Vertical asymptotes, I like to look at those like walls, like barriers. So imagine like you're this graph, and you have this barrier right here, and you want to keep going, right? But you got the barrier in the way. Like, what are you going to do? You got to keep going, right? You don't want to go like right into the wall, right? So you either are going to have to turn up, or you're going to have to dive down, right, to avoid the wall. So this graph, this particular graph, when it comes towards this wall, it says, I'm going up, all right? Now, what does it do on the other side? On the other side, as you're drawing it, it comes towards this wall, and if we just replace these with negatives, what would happen? All the answers would be negative, right? So instead of, if we plug in -1/2, we're going to get -2. We plug in -1/4, we're going to get -4. So it's going to dive down on this side, similarly to that one. And you've got that. Make sense? So at the end of the day, our graph is this piece along with that piece. That's the graph of 1 over x. Okay? Now, why would these be useful? Real world, right? Real world. So I'm gonna give you a quote from a movie, all right? And I want to see if anyone can name the movie. Now, this movie usually kind of ages me a little bit, kind of reveals my age. So you ready for the quote? See if anyone can get this. The quote goes, on a long enough timeline, the survival rate for everything drops to 0. I'll let you think about that for a minute. Has anyone seen that movie? On a long enough timeline, the survival rate for everything drops to 0. No? What? Shrek? Oh, no. I'll give you the main characters in the movie. Brad Pitt. Nope. I don't think Brad Pitt's in Mission Impossible. Tom Cruise. Brad Pitt, Edward Norton Jr. No? God, this is depressing. No? Fight Club? Has anyone seen Fight Club? We don't talk about Fight Club, but yeah. It's a weird quote from the movie because it's in an obscure part of the movie. Anyway, one of the main characters in the movie is an insurance adjuster, okay? And he's talking about cars. He's talking about defects in cars. Some of you, I'm sure, have at some point in your life owned an automobile, or family members own an automobile that's been recalled, that has some defect, and then you take it into the dealer and they fix it for free? Yes or no? Yes? I recently had to do that for airbags on a car. Okay, they say, oh, these airbags are defective, they'll just go off randomly and kill you. So we will replace them for free, right? Yes? No? Why are you disagreeing? What's that? That's not what happened.
No, that's never happened.
Oh, you never heard that before?
I've heard of it, but it's never happened.
Never happened to you? Okay. I think most Toyotas, older, like 2000, 2002 to like 2009 got recalled for all airbags. Anyway, okay, it's not important. The company that made those airbags went out of business, by the way, and they're right here on Wiseman in 1604. It used to be called Takata. They made the airbags. Okay. Anyways, okay, so I'm getting to the point here about rational functions. But the idea of a recall is this. Let's say that we own the company, right? So let's just say, I don't want to say which company. We're just going to be some car company here, all right? And we figure out that we have all these cars out here. Let's say we have, I don't know, just to make it easy, 100,000 cars on the road that are defective, right? And what's happening is that the defect is not, I mean, even though each airbag is defective, the chances that it's actually going to kill somebody is pretty low, right? It's happened maybe once or twice. So they know it can happen. So what they do is they say this. They say, okay, how much would it cost us? We have two options here, okay? Option A would be to do a recall. And if we do a recall, we have to take all 100,000 cars, right? And we have to bring them into the shop and replace the airbags for free. So that means we have to pay for the airbag replacement, right? We have to pay the labor to do that. And I know when I took my car in, all of that bill for that one car came out to be $800. Now I didn't have to pay it, but that was the cost. So imagine if you do this times $800, okay, what's that going to be? Let's see, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So how much is that going to be? What's that? 80 million? Yes? $80 million. Okay? That's option A. Option B is to have someone say, what's the probability that someone's going to die here? Okay? So let's say they decide that, you know what, 0.1% of the airbags are going to kill someone. And then what we're going to do is we're going to pay that family $2 million in a lawsuit settlement. Right? They're going to sue us because their family member was killed, right? And we're going to pay them $2 million to just be okay with that, right? So they say, okay, what's the probability of failure? They have someone that has to figure this out. They say there's 100,000 cars. We multiply that times the probability of failure, which would be I said 0.1%, which is actually 0.001. You have to move decimal point 2 places over, right? And then times, we're going to pay them each $2 million. So let's do that real quick. So 100,000 times 0.001 times 2. This comes out to be 20000. Hold on. I've got lots of zeros here. 3, 4, 5, 6. This actually comes out to be $200 million. So what's the company going to do? They're going to do the recall, right? But the crazy thing is, if this number turns out to be smaller than that number, they don't do the recall. So if your probability of failure is small enough, they've said, okay, we're willing to, I think when it comes to people dying, they pretty much have to do the recall. But like if it's something where you might, it might hurt you, but it's not going to kill you, then it's different. I think there's rules on that. But generally speaking, they look at these two things and compare them. And they're going to do what's more cost effective. They're not going to do what's more correct, like morally. You know what I'm saying? So anyway, in the movie, he talks about that. He actually talks about the equation they use for it. But he has this quote, on a long enough timeline, the survival rate for everything drops to 0. On a long enough timeline, the survival rate for everything drops to 0. So let's say that this is time. And let's say this is the probability that you're alive. And when we talk about this, let's talk about it in general. We're not talking about you. We're talking about just like a human being in general. there's a lot of factors. Are you male? Are you female? Do you live in the United States? Do you live in Africa? I mean, all these things will affect this. But let's just say you're born, and let's just say at time 0 you were alive. And we are not getting into a debate about when that is, okay? Because people will say, well, life begins here. And let's just say at time 0, whatever it is, you were alive. So the probability that you're alive is 100%, right? 1. I'm just going to say 1.0 for 100%. Okay, now, as time goes on, what happens? What's the probability that you're alive? It goes down. Now, I mean, most of the time, like when you're born, you're alive, right? But then, like, you got to get through those first months and stuff, and you can have complications as babies and stuff. But so your probability probably drops a little bit, and then it might come back up. So maybe by the age 10, like, you know, the probability that a human lives to be 10 years old, pretty good, right? Let's say here, this is 0.5. That's 50%. This would be like 25%. So let's put a number out here. How about 50? What do you think the probability is that you live to be 50? Pretty good or no? Pretty good, yeah? We all want to see 50 or no? Okay, I would say, I mean, it's probably higher than 50%, but let's just go with that, right? Okay, let's put another number out here. How about 75? What's the probability you'll live to 75? Well, if you're a woman, it's higher than a man in America, that's for sure. But it's still pretty good, right? Pretty good? I don't know, but it's dropped, right? It's dropping. I don't know, maybe 25% of the people live to be that old. I need to make that smoother. All right, let's put the next number up here. We're not taking into account any of these factors like, yeah. Oh, no, we are looking at modern medicine, okay? But like if we're comparing a person in America to a person in a place that doesn't have health care, then this changes. I'm just talking generally speaking here. Generally, the probability as time goes on is going to continue to drop, right? We're getting to like a fundamental issue here. What about 100? Probability that a human will live to 100. Pretty small, right? Pretty small. Now, my wife's grandfather, we just had his 101st birthday a couple of months ago. He's actually getting close to 102. So to 100, now we're starting to get to pretty small probabilities, aren't we? Okay, I'm going to put another number out here. 125?
Yeah, sounds like
Someone has? Really? Really, really small probability then? Really small probability. I'm trying to get closer. Okay, so let me put something out here. Let's put 300 out here.
hell yeah.
What do you think about that? 0? What do y'all think? We're talking about humans. 0? So I disagree. We're talking about a probability, right? Okay, so when you think about probabilities, what do you think the probability is that you could take a coin out of your pocket right now, flip it, and get heads, 2 times in a row? 50-50, right? Well, to get it twice. How about to get it heads? So you flip heads. I mean, it could happen, right? How about if you take a coin out of your pocket, you flip it 100 times? What's the probability of getting 100 heads in a row? Small probability? It could happen. So there is a probability, right? Just because nobody has lived to be 300 years old does not mean it cannot happen. Now, when we're talking about a probability, we're talking about an infinitesimally small probability. We're talking about probabilities that would be something like winning the lottery. That's a pretty small probability, right? How about winning the lottery every time you play it? Like you go play the lottery and you win it every time you play, right? Could it happen? Could it happen? It could, right? And the probability is extremely small. How about this? You play the lottery, you win it every time you play it, you get struck by lightning every day and you survive. Could it happen? It could happen. The chances are infinitesimally small. And this is what I'm trying to get at. This idea of a function dropping away to 0 without actually getting there is applicable in many, many, many things. Even because look, the problem with saying that 300 is 0 is that, well, then what about 200? Is 200 0? Like, where do you actually make it 0 then? Like, where do you make it 0? Do you see what I'm saying? Like, we can't make 125 0 because you said someone lived to be 125. So what is it, 126? See, we can't create an x-intercept here because we don't know where to put it. So, but what we can do is we can make it so small that it's essentially 0. Make sense? So these functions, you think about, oh, how about this? We'll do this one. How about your cell phone batteries? How about your cell phone batteries? Okay, so you go and, your cell phone battery, what's the chance when you buy your phone, your cell phone battery is going to take a charge and work and everything's fine? Pretty damn good, right? Although some suck when you get them right out of the box, but, so there you go. Probability that your battery is going to work, right? Okay, so what happens over time? Right? You have to charge it more frequently, right? It just doesn't work the way it did in the beginning. And they know that, right? The companies know that. And they try and make your batteries start to not perform well after, I don't know, a year or two, right? So they want this thing to drop away like that pretty fast so that you're now going, okay, time to get a new phone, right? You're happy with the phone, everything else works fine, but the battery doesn't keep a charge. So same sort of thing, a function that drops away to 0. Make sense? Okay, 15 minutes. So let's now go through and let me show you what the steps are to graphing rational functions. And then we're going to try and tackle one of these. I don't know if we can get into one of them now. But first step. On the next test, I'm going to allow you to have a formula sheet. Let's just say that right off the bat. And that way you can put, I told you I would give you this table. You can just have a formula sheet where you put this table. You can have all the steps for both graphing polynomials and rational functions, because it's a lot of steps to remember. So I'm going to allow you to have that, all right? First step, what do you think the first step is? Is it a rational function, right? Is it a rational function? All right. Now, I'm going to list the steps out right now. And some of the steps you're not going to have any idea what I'm talking about. Don't worry. When we get to the actual step, I'll show you how it's done. All right. So after we've determined that it is a rational function, what we're going to do is the first thing we're going to look at is finding the x-intercepts. Okay, now the x-intercepts, the graph I just showed you did not have x-intercepts, but these rational functions can have x-intercepts. I showed you one example, right? Rational functions can look really crazy. So it is possible to have these. And the way we do this is we set just the numerator equal to 0. And solve. You know how normally when we try and find x-intercepts of a function, we set the whole function equal to 0? Right? We set the whole thing equal to 0. Here, all we have to do is set the top one, the numerator, to 0. So look at this first one. Can you tell me, just by looking at this, what the x-intercept of this is? -1, right? Because if you set this equal to 0, the answer would be -1. Okay, so that's how we find the x-intercepts. The third step is to find the vertical asymptote. I'm going to say asymptotes because you can have more than one vertical asymptote. And the way you do this is to set the, what do you think? Not the numerator, denominator equal to 0 and solve. So remember in the picture I drew just a second ago, the vertical asymptotes, the vertical asymptote was that vertical dotted line, right? That vertical one. And that, remember it happened at 0? And 0 is where we had a bad thing in the function when we tried to plug 0 in. So this third step is saying, hey, look at the denominator, figure out where it's 0. Look at the denominator, figure out where it's 0. Anywhere where it's 0 is going to be where you have a vertical wall, all right? All right, so we've got x-intercepts taken care of. We've got the vertical asymptotes taken